Hello everyone and welcome back to tutorial 12 of MIE100, the dynamics course at the University of Toronto. Today we're going to be solving 3 questions on vibrations and time response, specifically free vibrations of particles. So this is all you're going to be doing this term. This is the last tutorial of the term. I know I'm uploading this very late, but I hope you can watch this before your exam, and if you have any questions, as usual, leave your questions in the comments below or email me. And yeah, thank you for sticking around in this term, and I hope you had a good term and good luck in your final. Okay, so starting with our first question over here, we've got to calculate the natural frequency of vibration if the mass is deflected from its equilibrium position and released from rest. Each pair of spring is connected by an inextensible cable. Evaluate your results for when the mass is 15 kilograms. The spring constants are 225 newtons per meter and 150 newtons per meter. Okay, so first of all, we need to find the length of each cable. So we're going to use the constrained motion of connected particles theory, which means that L is going to be equal to this length over here multiplied by 3. So let's call this length y. So it's going to be L is equal to 3y. Okay. Let's say that x starts from here instead of here. So let's shift it up a little bit. In this case, difference in length is going to be equal to 3x. This is how much the mass is going to move down. And we know that 3x is going to be equal to x1 plus x2, where x1 is the stretch of the spring in K1, so here, and this one is the stretch of the spring in K2, over here. Now let's draw a free body diagram to look at this question more clearly. So if we call this B and this over here A, we can start drawing a free body diagram for B and A. This is the normal reaction on the Y, and this is the tension in the cables. At A, the normal is going to be pointing down, and the tension is going to be pointing up. So we know that the tension in the springs, T, is going to be equal to K1 x1 or K2 x2. This is going to be our first equation, and this is going to be our second equation. So if we combine these two equations, we get x1 is equal to 3x over 1 plus K1 over K2. Now we draw the free body diagram of the mass over here. However, we're going to neglect the weight of the mass, so dynamic forces only. We've got tension pulling on this one upwards, pulling on her upwards too, and pulling on the pulley as well. These are all tensions and they're all equal. equal to this equation over here. Now, before we try to solve the Newton's second law, we're going to discuss some new material. If we have an undamped free vibration, like in our question over here, there's no damper, the simple harmonic motion equation is going to be as follows. X double dot plus omega n squared x is equal to 0. Now this over here we know is the acceleration. Omega n is the natural circular frequency. And x is the displacement. So this is a new equation. Every single equation that we have that has a vibration, we need to fit our variables into this sort of equation if it's undamped. Now, how do we find the natural circular frequency? The equation for the natural circular frequency is actually the spring constant over the mass all under the square root. So this is how you find the value over here. And then, for our question, to find the natural frequency Fn, it's going to be the natural circular frequency over 2 pi. So basically this only means that it's the number of cycles per unit time. These are all important equations. That we need to be aware of. Okay, going back to our question, if you look at this free body diagram and try to write a Newton's second law, it's going to be looking like this. The sum of forces in the x is going to be equal to ma, or mx double dot, which means that we've got 6 tensions pointing upwards, so it's minus 6t equals to mx double dot. And if we rearrange that, we get mx double dot plus 6t equals to 0. We can substitute our t with k1x1, which is and then once we've done that, we can substitute our x1 with this equation over here. So we're going to input 3x over 1 plus k1 over k2 into our equation instead. And here, we've turned this into a harmonic motion, a simple harmonic motion equation. So this variable over here is going to be omega n. rearrange it, it's going to be 18 K1 K2 over, oh, we forgot something actually. This isn't omega n. And this isn't a simple harmonic motion equation. If you look back, simple harmonic motion has no m before x double dot. So we actually have to divide the whole equation with m to get x double dot plus 18 K1 K2. I'm just putting this K over back here. M K2 plus K1 x equals to 0. And this over here is the natural circular frequency. So now that we found the natural circular frequency, this is squared, by the way. We just need to put it under the square root. And plug in our known values. To get omega n, or the natural circular frequency, is equal to 10.39 radians per second. If you plug that into our natural frequency equation over 2 pi, get the natural frequency equal to 1.65 hertz. And that's the final answer. All right, now with our question 2, we've got to determine the damping ratio of the system depicted in the figure. The mass and friction of the pulleys are negligible and the cable remains taut at all times. So if we look at the figure, we're going to notice here that there is a damper. So that means that our motion is damped. So let's discuss what it's going to look like when we've got a damped free vibration. When we've got a damper, we also have a damping ratio. And excuse me if I write it in a weird way, but this is basically zeta, or the damping ratio. It's going to look weird as well on printed, but this is going to be equal to C over 2m omega n, where C is the viscous damping coefficient. And m is the mass, omega n is the natural circular frequency, and that's it. Our simple harmonic motion equation is going to be equal to x double dot plus 2 zeta omega n x dot plus omega n squared x equals to 0. This is what we're going to try to fit our system into if we have a damping coefficient. Now going back to our question over here, we have a constrained motion on the pulleys. So with our constrained motion theory, we know that x2 is the one over here. Sorry, let me. X2 is moving over here. X1 is moving over there. So we know that x2 is actually equal to 2x1. There's one cable over here is equal to 2 cables over here. And that translates to velocity and acceleration too. So v2 is also going to be 2v1. And a2 is going to be equal to 2a1. Now let's draw the free body diagram with dynamic forces only. We're only considering the dynamic forces because in the equation, we already consider the mass when we do the sum of forces. So we need to discard the mass in the simple harmonic motion. We've got mass m2. We've got the spring pointing upwards. And tension pulling it upwards. And we've got mass m1. We've got two cables in tension pulling it upwards, and a damper pulling it downwards, actually. So if we consider the sum of forces in so let's call this system 2 and the system 1. If we consider the sum of forces in system 2, Fx is going to be equal to mx double dot, which is equal to minus t minus kx2, which is equal to m2x double dot 2. This is our first equation. Now if we consider the sum of forces in the first system, it's going to be equal to 2t minus cx dot 1 equal to m1 x double dot 1. Now if we sub in this equation over here into here, we can get 2t minus half cx dot 2 equal to half m1 x dot 2. This is because the velocity and acceleration of 2 is double the velocity and acceleration of 1. So if we sub them back in, they're going to be half cx dot 2 equals to half m1 x double dot 2. And the reason we're doing that is to actually combine equation 1 and equation 2 together and solve them simultaneously. So if we combine them together, we get m1 plus 4m2 x double dot 2 plus cx dot 2 plus 4k x2 equals to 0. Now if we remove those masses, we're going to divide them. So we're going to get x double dot 2 plus c over m1 plus 4m2 x dot 2 plus 4k over m1 plus 4m2 x2 equals to 0. This is our new equation. Now, this over here is equal to omega n squared. So we know how to get our natural circular frequency. We're just going to put it under the square root. And if we simplify that a little bit, we're going to take the 2 outside. So it's just going to be k m over m1 plus 4m2. But that makes it easy for us to find zeta, or the damping ratio, which is supposed to be c over 2m1 plus 4m2, because that's our mass part of the equation, multiplied by omega n, so 2m1 plus 4m2 over k. And if we rearrange this equation a little bit to simplify it, we get c over 4 k m1 plus 4 m2. And this becomes our final answer. Now for our third and last question of the term. A system is shown, link AOB, has mass m3 and radius of gyration ko, about point O. Ignore the friction and derive the differential equation of motion for the system shown in terms of variable x1. Okay, so this is actually radius of gyration, not the stiffness of the springs. And first thing we're going to do is draw a free body diagram. As usual, they're very important. And we're only going to consider the dynamic forces. So if we draw the free body diagram of this link AOB, there's going to be reaction forces on O, OX, and OY, and reaction forces on A. So there's force A pulling the mass at A, and a damper, C1, x dot 1, and at B, FB is going to also be moving it forwards, but the damper is also going to be moving it forward because it's damping the motion going this way. The distance between A and O is A, and between B and O is B, and the angle is theta from the vertical. Now if we draw those masses, M1, we have force Fa acting on the mass as well, and spring K1 x1 pushing it forward. While at mass 2, we're also going to find force Fb moving it forward, but the spring is actually pulling it back. So K2 x2 and we're ignoring all friction forces on the wheels. So now that we've drawn our free body diagrams, let's assume that this theta over here is very small. If theta is very small, that means sine theta is going to be around theta. And tan theta is also going to be theta, while cosine theta is going to be around 1. This is only when we assume that theta is very, very small. Now, for kinematic equations, if we consider this link with a distance a, an angle theta, and distance x1, we know that x2 over b is going to be equal to x1 over a, which is equal to theta, because a sine theta is equal to x1, and we're already assuming that sine theta is going to be equal to theta. So if you rearrange our equations, we're going to get this, which means that x2 is going to be equal to b x1 over a, x dot 2 is going to be b over a x dot, and x double dot 2 is going to be equal to b over a x double dot. X double dot 1 is going to be equal to a double dot theta. Now the reason we're doing that is because we want to find our differential equation of motion, or harmonic motion, in terms of x1, not x2. So that's why we're rearranging to make x2 the subject. Now that we found x2 to be the subject, we can now start with our kinetics. So the sum of forces of x1 is going to be equal to m1 x double dot 1 so that's going to be equal to minus fa minus k1 x1 is equal to m1 x double dot 1. And if we rearrange that to fit into our differential equations, we're going to get m1 x1 double dot plus k1 x1 plus fa equals to 0. That's our first equation. Now if we do the sum of forces in the x, we get m2 x double dot 2. If we look back here, it's going to be equal to fb minus k2 x2 equals to m2 x double dot 2. And if we rearrange that, we get m2 x double dot 2 plus k2 x2 minus fb equals to 0. That's going to be our second equation. And now we're going to do the sum of moments moving this way, clockwise. So sum of moments about O is going to be equal to IO theta double dot if you look at the lengths over here, it's going to be FA minus C1 x dot 1 multiplied by A. So FA minus C1 x dot 1 multiplied by A minus FB plus C2 x dot 2 multiplied by B. So minus FB plus C2 x double dot 2 multiplied by B. And for our moment of inertia, we have the radius of gyration and the mass. So it's going to be m3 ko squared theta double dot. And that's going to be our third equation. So if we simultaneously solve for 1, 2, and 3, we can get a final equation, differential equation, x double dot 1 plus a squared c1 plus b squared c2 over a squared m1 plus b squared m2 plus k naught squared multiplied by m3, all multiplied by x dot 1, plus, again, the same term, a squared k1 plus b squared k2 over a squared m1 plus b squared m2 plus ko squared m3, all multiplied by x1, equals to 0. And this is our final answer. And that's it. That was the end of our tutorial and also the end of the semester for this course. Thank you so much for watching and for leaving your likes and emailing me. I'll be available until your final, so if you have any questions at all, please email me at noor.doidar@mail.utoronto.ca or leave your questions in the comments below. Yeah, good luck in your final. I hope it goes well, and see you hopefully next year.